Okay, so an angle consists of two rays with the same endpoint. The endpoint is called the vertex. So here's examples of angles. Here's examples of angles. Two rays that have the same endpoint. We call that endpoint the vertex. What does it mean for two angles to have the same measure? So remember we talked at the beginning of the semester about objects and quantities, right? An object is something physical in the world, and then the quantity is a measurable attribute of an object. So that applies here. An angle is like an object. And then we have what's called the measure of the angle, and so that's a measurable attribute of the object or of the angle. So what does it mean for two angles to have the same measure? Any ideas? Yes, sir. Okay, so degrees is a way that a unit that we use, but so it doesn't matter what unit that we use. What does it mean that they have the same measure? Any thoughts? Distance apart of the rays. How far the distance is of the rays? Yeah. Symmetry. Okay, so distance of the rays apart is a common kind of thought about this. Let's investigate that for a little bit. So so look at this distance right here. Say right. So there's a distance of the rays, right? And then what about this? That distance. So which distance is longer? A or B? Which angle has a greater measure? A or B? A. So the distance isn't, we had to qualify it a little bit more. We'd have to say more. So distance doesn't, just distance from one ray to the other. Okay, so then you'd also have to talk about distance from the vertex. Okay. So this is it's kind of an elusive thing. Like, what does this mean for two angles to have the same measure? Okay? And so basically what we're asking really is when we measure an angle, what attribute of the angle are we assigning a value to? So what is the physical attribute that we're measuring? So we saw it's not distance across, but if you think of an angle like a door, right? Like, so one ray is the plane of the door, the other ray is the door, then how can we think of angle measure? How open it is, right? So we can talk about the openness of the rays, right? So the more open the rays are, the greater the angle. So order these angles from least to greatest openness. Compare with the person next to you. So which has the least openness, which has the greatest openness? Go. Okay, least openness is? C is the least open. So that's going to have the lowest value measure, okay? And then the greatest openness? B. That one will have the greatest angle measure, okay? So when we're measuring angle measure, we're measuring the openness of the angle. Okay, and so now the next question, how do we assign a value to the openness? How do we put a number on this? Or what's our basis for measuring angles, okay? So still, like, degrees is still just a unit. So it's not really the basis for measuring openness. It's just a unit that we use. So we really want to get at the heart of what is the basis for measuring angles. Okay, so in order to do that, there's a little activity here to design a pizza cutter. So here's two pizza cutters. Ever seen one like that on the right? The scissors? Okay, so the idea though is that we want to design, either one of these is fine, but a V-shaped pizza cutter, and we want to cut our pizza into 9 equally sized wedges or pieces. So we want to create the blueprint for the cutter. So whether it's the one on the left or the right, it's the same principle. We're trying to figure out the openness of the blades, right? The openness, or how open that little tray thing on the right is, okay? You don't have a protractor or any formulas, okay? But you do have things like pencil, ruler, tape, scissors, and string. So how are we going to design, so like the one on the left, how are we going to design that so that it'll cut 9 equally sized wedges of pizza? All right, I think this is in your workbook. No, so what's 360? Okay. So we're before that, right? So we don't know what degrees are. So we haven't talked about degrees. So this is on page. They still have it. Change it every. No. Okay, this isn't in your. It's not in your book anymore. So every year they change the edition, and too bad. But so just it's not in your book, but this is still a great activity. So we want to design this pizza cutter to cut the pizza into 9 equally sized wedges. All right. Again, what you have is a pencil, a ruler, tape, scissors, string, things like that. So take 5 minutes. Talk to the person next to you. How are you going to come up with a way to design this blueprint so that you make something like this that will cut exactly 9 equal pieces of pizza? Okay, something like this, or this is okay too. Exactly 9 equal pieces. Okay, so talk amongst yourself. And write out what your system would be. How would you come up with this blueprint? Okay. Does it look like a circle over there? Pretty close. Okay. Well, circles are going to be important for us, so we want them to look like circles. Okay, what'd you come up with? Let's see. Who is up? Morgan.
First I have a question. Is it going to be the same size pizza, or is it like specifically for this scenario? Is it not one in front of you, or two?
It shouldn't matter. So what your process that you do. So suppose you have this one in front of you, right here. Yeah.
So you take the string and you go all the way around it.
Okay, like that.
Yep.
Okay.
Find the circumference.
Yeah.
And then all you have to do is divide the circumference by 9. Then you find the inside edge.
Okay, so then you're going to unwrap that piece of string, and you're going to divide by 9, and get 9 equal pieces. And then what?
And then that would be the distance on the outside that you have to close.
Okay, so then you're going to put that back on the pizza. So just wrap it back around so you've marked off the 9 equal pieces, and then that will get it. Do we need to find the radius?
Find out how long.
We're just trying to figure out the openness of the cutter, right, to get exactly 9 equal pieces of the pizza. Okay, so this is really important. This principle is really important. How many people had something like that? Good. Okay, so this is a really important principle because what we just did is we figured out what 1/9 of the circumference was. That this pizza cutter is going to cut a piece of pizza that's yes, it's 1/9 of the pizza, but it's based on 1/9 of the circumference. So therefore, we're going to call this angle measure, we're going to call this 1/9. Or as a percent, like 11.1%, 11.11%. So this is going to be our basis for measuring angles, is looking at a fraction of their circumference, or a percentage of the way around. That's corresponding to an amount of openness. Okay, make sense? So let's summarize that. So the measure of an angle is based upon the percent or fraction of a full circular rotation. Percent or fraction of a full circular rotation, or the arc length relative to circumference. So what fraction of the circumference does the angle cut off? So the arc length is what fraction of the circumference that arc length that the angle cuts off. Okay, so according to this kind of way of thinking about angles, so what we would have is we have an angle like this, and then we think about its vertex at the center of a circle, and then we say what fraction of the circle, what arc length, what fraction of arc length of the circumference does the angle cut off? What would we call this angle? This is a 1/4 angle, or 25%. We're going to call this a 25% angle, or a 1/4 angle. Okay, again, you have given an angle, put its vertex at the center of a circle. And then, so what would this represent? It's not 1/3. I wanted this one. 2/3. 66.7%, or 2/3. That's a 2/3 angle. Okay, put the center at the vertex at the center of the circle. I want this one. So what angle is that? That's our 1/6 angle, or 16.7%. Okay, so there are different units for measuring angles, but no matter what unit you use, the kind of foundation of our measurement is going to be this. It's like, what percent of a circle do the angles cut off? Okay, so now that gives us a means of talking about degrees. So let's talk about degrees. What are degrees? What does an angle of one degree then represent? What does an angle of 1 degree represent? 1%? Someone said, yeah, 1/360th, right? So it's going to be an angle, we measure 1%, with its vertex at the center of a circle, what? Has rays that cut off an arc that's 1/360th of her circumference. That's what we're going to mean by 1 degree. It really comes from the idea of 1/360th of a circle. Okay, so then what is 36 degrees? So the angle 36 degrees means what? Tell the person next to you, what does an angle has the measure of 36 degrees mean? What does it mean? So 36 degrees means what? Joel? 100%? 36 degrees? An angle with 36 degrees?
Oh, you say 36?
Yeah, that's a 36.
Oh, I just mean 10%.
Yeah, so the rays are going to cut off, if you put the vertex at the center, the rays will cut off 10% of the circumference. 10%, or 1/10 of the circumference. That's what we mean by 36 degrees. Okay, so let's talk about it a different way. So degrees is 1 unit of measure for angles. So are those circles? Yeah, circles. Good. Okay. So here I've got some circles. And I want to, hope this works. There we go. Okay, do you see what just appeared there? I'll do it again, ready? Look, and there it is. So what am I illustrating with that bar that I just showed? The radius of the smallest circle. And what is the radius of the smallest circle? 1. Okay, so the radius of the smallest circle is 1. Okay, now keep your eye on that radius. Ready, here we go. So this is what we're going to do. I'm going to take that radius, and I'm going to pull it off its normal spot. And I'm going to wrap it on, I'm going to keep its length as 1 radius, and I'm going to wrap it on its circle. And they say, ooh, ah. Okay, so let me do it again. Wow, this is really important. So we got that radius. This is a normal way, you put the radius, you put it at the center, and it's the distance out to the edge. But if we pick that thing up, if we take it from its normal spot, pick it up, and wrap it on the circle, keep preserving its length, then it looks like that. Okay? What did I just show you now? I'm showing the radius of the middle circle, the second circle, which is a radius of 4. Here we go. I'm going to grab it, pick it off its spot, and wrap it on the circle. And finally, I just showed you the radius there of the largest circle, which is a radius of 6. Pick it up, take it off, and wrap it on its circle. Okay, so now you have 3 arc lengths, 3 arcs.
So if you multiply that by pi,
Whoa. So you're way ahead of us here. Something like that, right? But we're gonna explain all that from the beginning. So so 3 arcs. I want you to name as many things that you can that are different about those 3 arcs and that are the same. Okay? The color does not count as different. Okay? So list as many things as possible that are different, something mathematical, and the same. So you're going to make a list of things that are different and make a list of things that are same about those 3 arcs. Go. Talk with the person next to you. Okay, so what do we think for different? What is different about those 3 arcs? Length. Okay, the first one is 1, second one is 4. Okay, certainly the length of each arc is different. Good. Anything else that's different about? I already said that. Anything else that's different? Okay, yeah. So like the circle that they're on, right? So they're all from their own separate circle. The first one is from its circle of radius 1. Second one's from circle of radius 4. Third one radius 6. So the circle of origin. They all came from a different circle. They're all the radius of a different circle. Okay. What about anything else that's different that you think of? Okay, what about is there anything that's the same about the 3 arcs? The same about the 3 arcs. Brian. What's that? Okay, proportion to what? Okay, so the percentage of the circumference that taken up? Is that what you mean? Yeah, so the percentage of the circumference taken up by those arcs is the same. What else is the same about the three of those? Yeah. Okay, so the openness of the resulting angle. There's something else that's the same about those three arc lengths. They're all what? So before I even wrap them up on the circle, they're all one radius, right? They're all one radius of their circle. So we call that radius length. One radius length. Okay, so they're all different lengths in terms of the axis, measuring the units using the axis, but they're all, if you measured as a measure of radius, they're all one radius length. And then what we're noticing here is that if we wrap each radius length on its own circle, it's taking up the same percentage of the circumference. Okay, so let's see if I remember how to do this here. It's this one. So what I'm going to do is I'm going to use the positive x-axis. See the positive x-axis there? I'm highlighting it now. So that's going to be what we call the initial side of the angle. And what I'm going to do is I'm going to, I hope, right? Nope, not that. Let's see, raise it number 2. Let's try this. I didn't practice before I came. There we go. Why? All right, that's supposed to be longer. Sorry. There we go. Oh, here we go. That's what I want here. There we go. Okay. So do that again. So we're going to use one ray here as the positive x-axis, and then what I'm going to do, I'm going to sweep open an angle counterclockwise. And what you guys noticed was that all of those rays were the same percentage of the circle. And since we're saying that that's our measure for that's our basis for measuring angles, then it makes sense that we can conclude that using the radius of a circle then is a legitimate way to measure the openness of an angle, because no matter if we pick one radius length, no matter what circle you wrap one radius length on the circle, you're going to get the same amount of openness, right? So this is one radius. And this is one radius length. And this is one radius length. And they're all marking off the same angle measure, same amount of openness. Okay, so using the radius on a circle then is a legitimate way to measure openness because you're gonna get the same percentage of the circle, a fraction of the circle, and we said that's our basis for measuring angles. Okay, so this particular angle then, because this angle cuts off one radius length no matter what circle you look at, a real small circle or a really large circle, you're always going to, this amount of openness will always cut off one radius length. So then we're going to call this angle 1 radian. That's a 1. Okay, 1 radian. 1 radian is the amount of openness whose rays cut off one radius length of the circle. It doesn't matter what circle you pick, right? It doesn't matter what size circle. This openness of 1 radian will always cut off exactly one radius length. Okay, so then if I continue, so let's just talk here. So this is what we're going to call the initial side of the angle. It's the positive x-axis, right? Positive x-axis, or the initial side. And then we're going to also call it the 3 o'clock position on the circle, because it's pointing right at 3 o'clock on the face of a clock. Okay, and then what do? We swept counterclockwise. We're going to sweep counterclockwise from that initial side. So we're just getting the terminology down here. Because this is what your book, this is what we're going to talk about, and this is what your book will have. So you're going to start from an initial side, which is the positive x-axis, or the 3 o'clock position. We're going to sweep counterclockwise, and then this is going to be the terminal side, or the terminal ray. Of the angle. So that's going to be the jargon that we're going to use. And this is what we're going to be doing for the next 3 weeks. We're going to be sweeping angles counterclockwise from the 3 o'clock position to some amount of openness. Okay? One way to measure that is in degrees. We know 1 degree will be sweeping 1/360th of the circle. 36 degrees will be sweeping 1/10 of the circle. Okay? 1 radian sweeps what? Sweeps an angle that results in an arc length of 1 radius length. Okay? So 1 radian is going to be the angle that results in cutting off an arc length that's 1 radius length of whatever circle that is. Okay, so then this is, if you see down here, you see here's marking off 1 radius length, here's another. So how many radius lengths is that? That's 2 radius lengths. So the measure of that amount of openness in radians is 2 radians. Look at where it is. Look at where it is, okay? 2 radius lengths means it's an angle of openness that cuts off 2 radius lengths. That's 2 radians. So right now we're at 2. Right now I'm showing you an openness of 2 radians. Burn it in your brain. Okay? Let's do another one. Now I'm showing you, if you look on the smallest circle there, There's 1. There's 2. Now 1 more. So this is how many radius lengths? 3 radius lengths on all 3 circles, right? So on the blue circle, the radius is longer, but it still takes you to the same relative positions on the circle. Not there, further. There. Okay, so there's 1 radius length, 2, 3 radius lengths. So this is on the blue circle, 3 radius lengths. And on the red circle, it's still 3 radius lengths. And like this to there. Okay, so 1, 2, 3. So this amount of openness is 3 radians. So radians measures openness of the angle. It's an angle measure. Radius lengths is arc length. Okay? But here's the beauty of it. They're the same value. They're the same value, right? So however many radius lengths are cut off by the rays, that's the measure of the angle in radians. So radius length is arc length. Radians is openness of the angle. Okay? So they're talking about 2 different measures, but their values are the same. That's where we get radians from. We get radians from how many radius lengths are cut off by the rays of the angle. Okay, so I want you to make a little chart here. So I'm just going to take that off. All right. So now for this situation, so you've got purple, blue, and red. And we're going to make a little table here. Okay, R, that's for the length of the radius. Okay, theta, or let's go with this. S is the total arc length. And theta is the angle measure in radians. So for this situation that I'm showing you right here, I have a particular situation illustrated here. So for the purple, for the blue, and for the red circles, the arcs, you're going to put the values in here for the length of the radius, the total arc length, and the angle measure in radians. So this symbol theta is what we use for angle measure. So theta could be degrees, it could be radians, or it could be some other unit for measuring openness. Okay? S and R are lengths. Okay? Length of the radius, total arc length, cut off. So fill out this table. You can work together. Check with the people around you. And so what we want in the end is we want a relationship of R, S, and theta. That's what we're building towards here. Okay, so you're either making progress, getting help, or you're checking it with somebody else. Those are your three options. Okay, let's see, who's up today? John, how'd it go? How about let's do the purple row together here. What was the radius of the purple? Okay. Total arc length? 3. And what is our angle measure in radians? He wants 3. Agree?
Yes.
Cool. All right, how about Jackson? Blue circle, radius. Total arc length? 12. Angle measure in radians. What do we think? Good. Okay, let's see. Lewis. Red. 6. 18. Total length? 3. So remember that angle measure in radians? That's the openness, but it's the same value as what? What's 3, that angle measure in radians? It can also be thought of as 3 what? Radius lengths of arc length. Okay? So if we think of that number of radians as radius lengths of arc length, then we have all length measurements, right? We have the length of the radius, we have the total arc length, and then we have the number of radius lengths. So it's like a number of radius lengths, right? So what is the relationship then of r, s, and theta? You're all packing up at the most important part. What is it? R times theta equals s. So why does this make sense? Because if you have the radius length times, how do we think of this as? How many of them, right? How many radius lengths you have. That's essentially what the angle measure in radians is. This is the most important point of the day. That number, that's the angle measure in radians, is essentially how many radius lengths we put around the circle. And how many did we do? In all cases, it's 3 radius lengths. Number of radius lengths. So this makes perfect sense that if you take your radius lengths and you multiply it by how many of them you have, you're going to get the total arc, right? So that should make perfect sense. The radius length times how many you have gives you the total length of the arc. That should make perfect sense. 10-10 if you got recitation today to start the test.